Richardson extrapolation combines two trapezoidal estimates taken at different step sizes to cancel the leading error term, turning an a-squared method into an h to the fourth method for free. It's still just the trapezoidal rule. Compute it twice at two different step sizes and mix the two answers in a way that cancels most of the error. The trapezoidal estimate T of h has an error expansion that only involves even powers of h. No odd powers show up. That comes straight from the Euler-Maclaurin formula. The constants C2, C4, C6 depend on derivatives of f at the endpoints, not on h itself. Evaluate that same trapezoidal rule again, but with half the step size. Every power of h in the expansion shrinks by that same power of 1/2. H squared drops to a quarter, h to the fourth drops to a 16th. Here's what those two estimates look like geometrically. On the left, one crude trapezoid spans the whole interval. On the right, two smaller trapezoids meet at the midpoint, already tracking the curve's dip much better. We want a combination, a times t of h plus b times t of h over 2, that reproduces I exactly, at least to leading order. That means the constant terms have to add up to I, and the a squared terms have to cancel. Two conditions, two unknowns, a and b. Solve that small linear system and you get a equals minus 1/3, b equals 4/3. Plug those coefficients back in and the h squared terms cancel exactly. What's left over is a new error term proportional to h to the fourth. Two h squared estimates have just combined into one h to the fourth estimate, and all it took was arithmetic on numbers you'd already computed. Same test function as the Newton-Cotes video, so the results are directly comparable. Define f of x as a function of x, returning x squared. Build the node array for 4 segments and apply the composite trapezoidal formula, exactly as in the Newton-Cotes video. Call the result T4. Repeat with twice as many segments to get T8. Then combine both estimates with the Richardson weights 4/3 and minus 1/3 to get R. Sweep n from 2 up to 32, doubling each time. At every level, compute both the raw trapezoidal estimate and its Richardson extrapolated partner and compare their errors. Same data, same trapezoidal rule underneath. The only difference is combining two estimates. The slope on the log-log plot jumps from 2 to 4, 16 times the accuracy every time n doubles instead of 4. Now specialize to the smallest possible case, one segment for t of h, and two segments for t of h over 2 with m as the midpoint of a and b. Substitute both formulas into the Richardson combination and simplify. The algebra collapses to exactly the Simpson's 1/3 rule formula from the Newton-Cotes video. Same weights, 1, 4, 1, same h over 3. So Simpson's rule isn't a separate method at all. It's what you get from applying Richardson extrapolation to the trapezoidal rule exactly once, at the smallest possible step size. Richardson extrapolation, week 3.